So hello and welcome friends to our channel Intro Mech, and we are learning about the metal casting process. So today we will see the different parts and how the gating system is designed. So we have in the last lecture we have seen the pouring basin, the sprue, runner, ingot and all these things. Now we will see them into the detail. So let's consider let's have a pouring basin. Okay, so this will be your this is my cavity which I want to fill. Okay, now this is my pouring basin. Okay, so this is our pouring basin in which the molten metal is kept. Now we have a small metal strip which is made up of the same material as that of the casting. So we place it here and we fill the molten material here, and this cavity is provided to have impurities, so that the heavy impurities gets accumulated here and will not go into the cavity. So this metal strip will get melted, and because of that we get a uniform flow of the material, and that's why this metal strip is kept here. So this is our sprue. Okay, now this material comes into this runner, and this from this ingot it enters into the cavity. Okay, so now the pouring basin, we understood that it is the basin in which the molten material is kept. Okay, now the sprue is the connecting media from the pouring basin to the runner, and the design of a sprue is very important to avoid the aspiration effect which we have seen in the earlier session. So for avoiding the aspiration effect, this sprue is designed with the trapezoidal it is designed with the tapered shape. Okay, and it has a uniform tapered shape to minimize the aspiration effect. And let's consider the area of the sprue. Let's consider is AS. Okay, so the cross sectional area of the sprue, we will consider it as a AS, which is the minimum area of the sprue. Now the runner, so runner is taking this molten metal from the sprue to the cavity. Okay, so the runner is having shape of trapezoidal, and it is a uniform trapezoidal cross-sectional area. Now the reason behind it is the trapezoidal shape has the highest coefficient of discharge, so that's why it can carry the molten metal efficiently to the cavity, and that's why its shape is kept as a uniform trapezoidal shape. Okay, now the ingot is also having the uniform trapezoidal shape, and it is the entry to the cavity. And the runner area, let's consider it as a AR, and the ingot area, let's consider it as a AI. Okay, so these are the three areas. And now what is gating ratio? The gating ratio is nothing but, let's consider it as a gating ratio. It is as given as the ratio of the area of the sprue as to area of our riser as to area of ingot. So this is very important, this gating ratio, because from this gating ratio the different gating systems are designed. So this gating ratio is very important. Now apart from this, there are some accessories which are provided. So the accessories, if we consider, then first is strainer. So strainer is nothing but some kind of filter to avoid the impurities to go through. Then splash core is a piece which is added to avoid the sand erosion in this case, because the fluid is suddenly coming here, so it might happen that there is a sand erosion here. So to avoid that sand erosion, the splash core is provided. And the skim bob is like the this is our runner, so it has given a shape like this, so that when the molten metal is coming, the light particles, the light impurities can the heavy particles will get accumulated here, and they will not get into the cavity. So that's why this skim bob is given. Okay, this is skim bob, and this is our splash core. Okay, and this is our strainer. So these are the accessories which are provided along with the design. Now we'll see the gating system. As I told you, the gating system design is very important, and it is based on different parameters. Like what the first parameter is based on the pressure above the molten metal in the pouring basin. Okay, so non-pressurized system. So if we consider this pouring basin, okay, so if it is open to atmosphere, now molten metal is here, so we are keeping it open to the atmosphere, so the pressure here is P atmosphere. Okay, and the pressure in the pouring basin, let's say C, let's say P. So in non-pressurized system, this P is equal to P atmosphere, because we are not pressurizing the fluid and we have kept it open to the atmosphere. But the biggest disadvantage here is the highly reactive metals like aluminum, magnesium. They can easily react with the oxygen in the atmosphere and gets oxidized. So we cannot provide this non-pressurized system to such a highly reactive materials. And the gating ratio for this system is 1:2, 4:4, or 1:2, 2:2. So this is the gating ratio for non-pressurized system. Now the pressurized gating system name itself suggests that the pressure acting on this fluid is greater than the atmosphere. So for that purpose, it is covered from the top side, and the required pressure is kept on the liquid. Okay, so it is closed from the top, so that the pressure acting will be, let's say, P1, and this is our P. So the P1 is greater than P, and that's why it is called as a pressurized gating system. And the ratio of the pressurized gating system is 1, let's say is 1:2, 2:1. So it is 1:2, 2:1. So we have seen what is this is nothing but the area of our sprue as to ratio of area of our runner as to ratio of our ingot. So this is the pressurized gating system. And the another advantage of this system is very important. Let's understand this. Now the velocity of the flow, we know, is given as root 2 times g into ht. This is the head which is acting and which is responsible for this velocity. Now if we want this velocity as the highest, and if we keep it to the atmosphere, this ht is larger, so the size is larger. But instead of that, if we go for a pressurized gating system, because of the high pressure, this height can be reduced. So this is another advantage of this pressurized gating system. Now let's see the another how we can classify it on other basis. Now we are going to see a very basic thing. So how we can calculate the pouring time, so how much time it is required to the cavity get filled. So it can be calculated as the volume of our casting, and the flow rate of the material. So at what flow rate it is entering into the cavity, and the volume of the casting. So from that we can calculate the pouring time. Okay, now we all know that the flow rate Q is nothing but area into velocity. Now we require the velocity to be maximum, so that's why we can have a area to be minimum, so that we can have a velocity maximum. Now this minimum area is called a choking area. This is called as a choke area, and this choke area, let's say AC, is minimum area out of, we have three areas. Okay, we have our sprue area, then we have our runner area, and we have our in-gate area. So whichever is the minimum of this, that will be the choke area. So if we consider this choke area, then we will get the maximum velocity which is required. So we always have to go for this choke area, so that we can write it as Q is nothing but AC into V max. Okay, so we have to consider the choke area. So now where the getting system, where the material is entering into the cavity, from that point of view, the getting system can be divided into another three parts. The first one is top getting system. So in the top getting system, the material is poured from the top section, and then it is entering into the cavity. Okay, so this is our cavity, and let's say this is our total height which is acting over this cavity, which is responsible for the velocity. Now this height is total height, considering this pouring basin height plus sprue height. Okay, so by combining these two heights we get the HT. Now in this case, our pouring time, let's say PT, will be our volume of casting upon divided by flow rate. Now the choke area into velocity is √2 times G into HT. Okay, so this HT is the total height, and that will give us this will give us the maximum velocity, and that's why we will get pouring time as this formula. Now this pouring, now for the top getting system, is the simplest system, and it gives the minimum pouring time. So out of all the getting systems, the top getting system, in the top getting system we get the minimum pouring time, as the velocity which we get is maximum. The head acting is always HT here, and that's why we get the maximum velocity. Okay, now we will see the bottom getting system. Now the name suggests itself suggests. So in this case we have a pouring basin, and the sprue, the material is getting filled from the bottom. Okay, now the thing is, as the material is getting filled from the bottom, the effective height which is acting on this fluid is varying, because initially when you start filling, the height which we are getting is total HT, but as this fluid level starts increasing, let's say by layer 1, 2, 3, this effective height from the pouring basin, let's say HE, it goes on reducing, and because of that the velocity keeps changing. So in this case we can't have a maximum velocity, but we have to go for the average velocity, because the velocity is changing layer by layer. As the material is getting filled, this height is reducing, and the effective height which we are getting is will be, let's say H1 will be HT minus HE. So at that moment H1 will be ht minus he, and that's why the velocity will be root 2 times g h1. Okay, this is at, let's say, at one moment, at initial moment my velocity will be maximum, which will be corresponding to ht, because ht is maximum. So we have to consider the average velocity in this case, and that's why we can write as pouring time is nothing but our volume of casting divided by choke area into V average. So this is very important in this case, because we have to consider the average velocity. As I explained here, the velocity is changing. Now the parting and the pouring time is more as compared to top getting system, because we can see here the velocity is average velocity, so that's why the time required is more. Now the third one is parting getting system. Now we have seen that we can divide, this is the parting line, and the top one is our cope and drag system. So if I am making my material entry at this section at the parting line, this is called as a parting line. Okay, this is my parting line. So I am making the entry of material at this parting line. Okay, so what will happen here, there is a combination. Okay, so for this one it will act as a top getting system for one, and for this one it will act as a bottom getting system. For first one it will act as a top getting system, okay, because the material is entering from the top, and for second one it will act as a bottom getting system. Okay, so here it is the combination of both the systems, so we have to combine the time required for both the getting systems. So our total pouring time will be pouring time of 1 plus pouring time of 2, so that will be our volume of casting at section 1. Okay, so this much volume will get filled with the help of top getting system, and here area choking, and here I am getting the maximum velocity because the total head is acting for this volume. Okay, then for P2, so this is bottom getting system, so here we know the volume 2 is getting filled with the bottom getting system, and here we have a choke area into V average. As we seen here, for this portion the material is getting filled and the effective head is varying, so velocity will be V average. So total pouring time will be addition of both this system. So these are the basic getting systems which we have seen here, and how we can calculate the pouring time in these systems. So we can finally see and conclude that the pouring time required in in the top getting system is top getting system is minimum, and for this top getting system is minimum. Okay, and for bottom system it is maximum, so we can write as PT top is lowest, then PT parting, and then the PT bottom will require the maximum time to fill it. So this is the case, we will require the minimum time pouring time in case of top getting system, then the intermediate time for the parting getting system, and maximum time will be required in case of bottom getting system. So here we have finished the getting system design, and in the next lecture we will see the solidification time and other factors which are related to the design of the casting. So thank you, and if you have any doubts, please do write into the comment section. Until then, be safe and stay happy. Thank you.